Hello everyone. In this video we're going to discuss about parallel plate capacitors. In our previous video you will remember that we discussed about single conductor capacitors, and more specifically we came down to a spherical capacitor. Now with a spherical capacitor there are some very severe limitations. A spherical capacitor has very tiny capacitance and therefore it can hold very tiny amounts of charge. Also, not just the charge is small, but the corresponding amount of energy stored by a spherical capacitor is also very, very small. Now, since we are interested in storing larger amounts of charge, larger amounts of energy, spherical capacitors, with single spherical capacitor aren't really good enough for any practical kind of applications. Also, you will realize that with a spherical capacitor involving a single spherical conductor, the potential energy that is stored in the electric field is stored all the way up to infinity. From the surface of the conductor to infinity, the energy is stored in the electric field. And since this energy is stored in an electric field that is spread all the way to infinity, the energy is spread in an infinitely large amount of space. You can think of this as having a farm which has a very small produce which is spread in an infinitely large or very, very large area. Since the produce is spread over a very, very large area, it's very difficult to bring it together and make anything useful out of it. So spherical capacitors are pretty much without much practical use. Therefore, what we need is some practical kind of a capacitor, and what we come up with is capacitors having two conductors instead of one. So if we have two conductors instead of one, both placed reasonably close to each other and connected to the two terminals of a battery, then their energy is stored in the limited space between those conductors, and also the capacitance is relatively much larger than spherical capacitors. Now, these capacitors with two or more conductors involve higher capacitance, greater ability to store charge, and therefore also the ability to store greater amounts of energy. Now these capacitors come in various shapes and sizes, the commonest being the cylindrical form. Two coaxial conducting cylinders connected to the two terminals of a battery. Then comes what we call a spherical capacitor, which has two concentric conducting shells connected, of course, to the two terminals of a battery, and that also has higher capacitance than a single spherical capacitor, and also greater ability to store energy. Now the third kind and the simplest to study are the parallel plate capacitor. Now parallel plate capacitors involve two parallel plane conducting sheets held at a small distance from each other and connected, of course, to the two terminals of a battery. Now a parallel plate capacitor is actually the easiest to study and a great example for studying the ideas related to capacitors, and therefore it is the one that's been kept in your syllabus so that you develop a good understanding of capacitors, starting with parallel plate capacitors, and you can easily build on that understanding for other shapes. So here we go and discuss a parallel plate capacitor. Now the figure you notice on my right is the essential construction of a parallel plate capacitor. It consists of two parallel conducting plates of area A each, held at a very, very small distance from each other. The distance d between these plates has to be very small in comparison to the linear dimensions of these plates. So for example, this d, the distance between the plates, has to be much, much smaller than both the length as well as the width of these plates, and only then the capacitor can function effectively. So this is the construction of a parallel plate capacitor. We move on now and discuss about how we get it to acquire charge and energy. Once we connect these plates to a battery, we connect, of course, the plate on the left to the positive terminal and the plate on the right to the negative terminal. So the plate on the left has a higher potential than the plate on the right. And therefore, as we move from left to right between the plates, the potential decreases. And we all understand very well that potential decreases as we move in the direction of an electric field. So the decrease in potential from left to right is indicative of the fact that there has to be an electric field in the region between the plates, and this electric field has to be directed from left to right. Now, these electric fields, we all know very well, cannot just appear out of thin air. The electric fields have to be produced by charges, and therefore charges have to appear on these plates. Of course, there has to be a positive charge on the plate on the left and a negative charge on the plate on the right, because the electric field is directed from left to right. So charges now appear on these plates, and these charges are directed from these charges are positive on the left plate and negative on the plate on the right. These charges produce our electric field, and in that electric field this capacitor stores potential energy. Now, what's the source of these charges? Where have these charges been picked up from? Now this figure here to my right shows that the battery actually transfers an amount of charge Q from the plate on the right to the plate on the left. So since both the plates were initially uncharged, the withdrawal of a charge plus Q from the plate on the right ensures that it now has a charge minus Q. Since it had zero charge, and when you subtract Q from 0, you end up with minus Q. And therefore this plate now, plate on the right, has a charge minus Q, and the plate on the left has a charge plus Q. This ensures your electric field directed from left towards right. Also notice that the charges on both these plates are equal and opposite, and therefore the total charge still remains 0. A little more about the distribution of these charges. Now look at the figure below the figure on my right. There's a figure here on my right, and just below that figure there's another figure which is something from our past, one of the videos I did earlier on conductors and capacitors. Look at the two plates. What we have essentially done is we've given a charge plus Q to the plate on the left and a charge minus Q to the plate on the right. If we take this plus q and minus q as q1 and q2 and use the formula we had arrived at for distributing charges on the surfaces of two parallel conducting plates held at a small distance from each other, then the left surface of the plate on the left has to have a charge q1 plus q2 by 2. And since q1 and q2 are plus q and minus q respectively, the plate on the left has a charge 0 on its outer surface, and the entire charge plus q appears on the inner surface, and similarly the entire charge minus q on the plate on the right appears on its inner surface as well. So we've understood why the charges on the two plates have been distributed the way they've been distributed. And if we now look at the next figure, which now appears again on my right, this figure shows the electric lines of force which start at the plate on the left and terminate on the plate on the right. We are very well aware that electric field lines start or originate at positive charges and terminate at negative charges. And that's exactly what is happening in this figure. Also, notice right at the ends or right at the edges of the plates at the top and the bottom, the field lines aren't exactly straight there. They're bulging out a little. And this effect of bulging out of field lines is called the fringing effect. Of course, in our calculations, we're going to be ignoring this fringing effect because it takes place in a very tiny amount of space and therefore is pretty much irrelevant to our calculations of capacitance and the energy stored in the capacitors. And therefore, for all practical purposes, this fringing effect is to be ignored. Now look at the fourth figure, which has just appeared below the figure on my immediate right. And in this figure, what I've shown is, I've shown the electric fields due to the two plates. I have called the plate on the left as plate 1 and the plate on the right I have called plate 2. Now, the electric field due to charge on plate 1, which produces a plane sheet of charge, that electric field is towards right because it's a positive charge, field is away from it. And the magnitude of this field due to this plane sheet of charge equals sigma by 2 epsilon naught. Now sigma of course is q by a, and therefore the field will be q by 2 epsilon naught a. Similarly, the field due to the charge on the plate on the right is also q by 2 epsilon naught a and is also directed towards right because this time the charge is negative. So the total electric field or the net electric field between the plates is the sum of these two fields, E1 and E2. E1 and E2 being q by 2 epsilon naught a, when they are added we end up with q by epsilon naught a, which you will recall from our earlier class on the behavior of conductors. We learned that the net electric field just outside the surface of a conductor will always be sigma by epsilon naught, and that's exactly what we have arrived at after adding the fields from both the surfaces of the plates. So it all gels in perfectly here. The fields of individual plates are sigma by 2 epsilon naught each. The net field between the plates is sigma by epsilon naught, that is q by epsilon naught a. Now, once we multiply this field q by epsilon naught a, you go further down in those calculations and you will see that the potential difference between the two plates will be E, the electric field, the net electric field between the plates, times the distance d between them. So E times d gives us the potential difference V. This V therefore equals, you look at the equation just below that, the potential difference V now is equal to QD by epsilon naught A. So we have V equals QD by epsilon naught A, and therefore Q equals epsilon naught A times V by D. Now let's compare this equation with the general equation which defines capacitance, which is Q equals C times V. And when we make this comparison, it becomes pretty obvious that the capacitance C equals epsilon naught A by D for a parallel plate capacitor. So we have derived in using a very simple method, we have derived the formula for the capacitance of a parallel plate capacitor, and we will now move on and discuss about the energy storages. Now we are already aware of the formula for the energy stored by a capacitor. Now in case of a parallel plate capacitor, of course, the total charge stored by the capacitor is really zero, because we have plus Q and minus Q on both plates. They add up to zero. The charge of a parallel plate capacitor is described as the magnitude of charge on any one of the plates. The potential energy stored in the capacitor remains the same, that is Q square by 2C. That's equation 1 over there. Now, if we substitute C here, what we will end up with is Q square by 2 epsilon naught A by D. And on some minor manipulation, what we'll be doing is we will multiply and divide by epsilon naught as well as A. And when we multiply and divide by epsilon naught A, you will notice as we move further down these calculations that the potential energy stored becomes equal to half epsilon naught E square times AD, E being the electric field between the plates. You got that equation, right? So that AD right at the end, notice that AD. Now what is this AD? This AD is the volume in which the electric field exists between these plates, right? The area of the plates is A, the distance between them is D, and the electric field exists exactly between the two plates, and therefore the space, the volume of the space where electric field exists is A times D. So that's your volume V, and when we divide both sides of the equation by volume V, we will get U, the potential energy, divided by volume V, and that's the potential energy per unit volume, or the potential energy density represented by small u. And this small u, you can easily notice, equals half epsilon naught E square. I guess that's your equation 2 there on your screen. So this is the formula for potential energy density. In fact, this is a general formula in nature. Wherever an electric field E exists, there is potential energy associated with its existence, and the energy associated with a unit volume of space where an electric field E exists, that potential energy per unit volume of space is half epsilon naught E square. This is true for any electric field anywhere in space. And so now we move on and discuss about the calculations of energy conservation in the process of charging of a capacitor by a battery. Now have a quick look here. The capacitor has acquired a charge Q because the battery has transferred a charge Q from the plate on the right towards the plate on the left. Easily noticed, right? So charge is flowing through the battery, and how much? Q, which is CV, and it flows from right to left in the battery. What happens is the battery has now increased the potential of this charge by an amount V, and therefore the battery has increased the potential energy of the charge by Q times V, Q times the increase in potential. Now QV is the increase in potential energy of the charge, and therefore the work done by the battery is QV or CV square. Intriguingly, the energy stored by the capacitor is only half of that amount, that's half CV square. So where does the rest of the work go? Well, the rest of the work is actually being is converted into heat, and it's so often in physics that we find that when the balance of energy isn't quite right, we will end up finding heat being produced somewhere, and that's exactly what is happening here. The battery performs more work than the energy stored in the capacitor, and this happens because when charges flow through the wires, heat is produced. When charges flow through wires, currents flow through wires, and when currents flow through wires, heat is so often the result. As you studied even in earlier classes, I guess a class 10 was when you learned that when currents flow through wires, heat is produced. And that brings us to the end of this interesting little video on parallel plate capacitors. In our next video, we will be talking about combinations of capacitors, series combinations, parallel combinations, and also we will study some techniques which we use for calculating equivalent capacitances of larger combinations of capacitors. So that's coming up in one of our next videos from this channel. Thank you very much for watching this video. Like, share and subscribe if you benefit from the content that you view on this channel. Please keep supporting the channel, and also keep sending your feedback. This is the first video with this new format, and I would like to certainly receive your feedback on how you found the format of this video. Was this better than the earlier videos? Worse? Please do let me know in the comments below. Thank you.